Hello community! You ask, why is there this hype on Superhuman today? Let's have a look. Now, let's start a deep dive. We have a query, we have an LLM, and this generates an answer. And we have hundreds of trillions of tokens and sentences, and we train this, and we refabricate hundreds of trillions of tokens and sentences. We have a large language model. Now, we do this here in a sequence. And of course, the sequence, we have a pre-training where we have a neural network of tensor weights. Then we do the fine-tuning for a particular domain. And then we have here a DPO alignment to have a nice friendly behavior of our LLM. Beautiful. Now, if the LLM encounters something where it has no actual data, the LLM calls out to a database or to the internet to retrieve here some information, comes back, combines with its parametric knowledge, and generates an answer. Beautiful. We call this Retrieval Augmented Generation Rag. That's it. Now, people get a little bit excited about RAG, so let's have a look at this. You can make the retrieval process real complex. You can make the augmentation process real complex. And you can make the generation process, here our LLM, really complex. So let's have a look. It is easy to understand. Here on the right-hand side, we have the complete knowledge of the internet here. And on the left-hand side, we have also the complete knowledge of the internet. And you might say, what? Well, it's easy. Here, we have this knowledge encoded here in a neural network, in a transformer architecture, where we have learned tensor weight structures, new topologies. And here on the other side, we have the same content, the complete knowledge of humankind, but encoded knowledge in vector spaces, in mathematical spaces. And this here we call the retrieval process. Here in the middle, you have the augmentation process where it comes together. And then we have the generation process. So not only the knowledge here from our LLM is used, but the knowledge here of all the databases and everything that has actual brand new data is here augmenting here our result in the generation. So yeah, we are really so intelligent to include here, to encode here the complete knowledge of humankind at first in a neural network structure, and then we encode it in a mathematical vector space of 1024 dimension or higher. Welcome. Now, these high-dimensional embeddings are beautiful, but we have to reduce here the dimensionality of those vector spaces to have fast mathematical calculation. So we want a lower dimensional vector space to perform our mathematical calculations like a similarity operation, a cosine similarity, to extract here the semantic close-by information from our query vector. As easy as this. So you see a lot of simplifications. But on the other side, we also have simplifications. Now, with our tensor structure, we do the mathematical calculation in a 30-bit or 16-bit precision. However, we can make it easier. We can reduce the complexity with a quantization, and we just go to an 8-bit or a 4-bit representation. Please note, currently there's a nice research going on with a 1.58-bit representation. Plus, not only the precision we can reduce, but we can also find new ways to perform our tensor algebra. So you have here parameter-efficient fine-tuning with the low-rank adaptation methodology. And if you combine this here, we have a quantized LoRa. Beautiful. Remember, on the left side, everything operates in a vector space. So whenever you have new data, the vector space, either you add data or you reconfigure your complete vector space. There are a lot of vector spaces you can buy from commercial sellers. And if you have an optimized vector space for your domain, for your topic, for your task, this is a really valuable vector space. And then, when we have this vector space, we reduce the dimensionality down to something where we can have here a fast mathematical operation on this. So you see, the retrieval can be complex, the augmentation can be complex, and all of this leads us now to something beautiful, to agent, and in particular to multi-agent system. Now, you might ask, what are agents? Agents can be in different forms. Here on the left side, you have the simplest agent, a simple rule-based agent. Now, this little agent has this easy task. I tell the agent, hey, you, if your input stream contains this particular stream of characters, you do operation A. If the input stream contains a different string of characters, you do operation B. So I have a rule-based agent created, and this little agent will perform his task. But of course, in the time of AI, you can have a super intelligent agent with multiple large language model or whatever inside that combine, that communicate, that had access to internet, to different databases. The sky's the limit how complex you can build your agent. If you're looking for a definition, here you have one from Wikipedia. So let's have a look if we have a multi-agent scenario. It is the same. We start with a query. The LLM has no data and it asks an agent. The agent goes to his SQL database, asks the database. Database says, sorry, no data. The agent says, no problem. I ask another agent I have contact to. And this agent here is an intelligent agent with a large language model integrated and access to a vector database or to the internet. So this agent goes out, finds somewhere some information, has this information, retrieves now this information, and now either it says, okay, this is it, and I provide this information, or the agent decides, okay, and now I provide this to a vector store, I integrate this in a vector store, I modify the query a little bit to the vector store, and then I see what is my result. So what do I get back from this vector store? And this is then a result that comes back, and now the agent says, great. And now as an option, you can have a re-ranking of your result that you get back. Now the re-ranker is something really interesting because it looks again at the data and evaluates the data a second time. And maybe the re-ranker says, you know, the first result you came back, this is not really what I've been looking for. I choose number 3. So this result goes back to the first agent, and the first agent might have a logic filter, any filter at all that you program. And after passing the filter, it goes now here to the primary LLM, and it is augmenting the parametric knowledge of our LLM. And then the whole LLM generates an answer, a RAG system. Let's have a look at the worst case scenario. What could happen if it goes wrong? Let's say my query is, I need a specific information. LLM goes to the agent says, okay, database has nothing, goes to the second agent, and the second agent finds here the information somewhere. Now, 28.2 is now returned as an answer. However, during the re-ranking, and let's say we have a vector store, a vector embedding, and real close to this particular vector embedding, we have a dominant vector. And this dominant vector now in the re-ranking algorithm is here overriding here the result of our 28.2, because it happens that in the re-ranking, the system decides, hey, this is the primary alpha vector. So now the re-ranker returns here 343. This is the reason why we have a re-ranking and not a, for example, quantum encoded or quantum encrypted channel back to the LLM. We add the intelligence of each and every agent to it. So agent 1 receives now 343 years, and its logic filter says, okay, let's say the age of this person is 343 years old. That's a little bit strange. And whatever happens in agent 1 decides, either from its training data or whatever, that real close, there's a similarity between 343 and 14 for this agent, for its training data. So a logic filter now is the output, 14, and 14 now augments the parametric knowledge and generates an answer. Now it might happen at this step, the LLM is now hallucinating. And instead of 14, which is not at all what was in the database or in the internet, the LLM hallucinates and generates an answer of 242. This is what we do not want to happen. But this can happen because we are operating here with autoregressive system, we are operating here in a transformer architecture, we are operating here with probabilities, we're operating in mathematical vector spaces. This can happen in the worst case scenario. So what we need logic. We need somebody who understands what's happening. Either this somebody is our LLM. So we have here the internal logic that we use. Let's say if it's GPT-4, beautiful. Or you might say, hey, in addition, I ask Claude, hey Claude, could you provide us your logic so we can have a check? Beautiful. Now, what we developed over the years is here reasoning capability. So we want to reduce the complexity of the query that comes in and process now each simple task individually. So we decompose the high complexity to a set of low complexity problems and solve each task individually. We can do this with a lot of methodologies. We have a chain of thought to a self-RAG system. There are more than 20, 25 methodologies you can apply for this. Plus, also C-RAG, whatever there is. After the reasoning, you want to make sure that this is really the right reason. So you start to evaluate the result. So either you can ask the system to self-evaluate the correctness of each individual simplified task by a self-assessment, or you go here to an external LLM or whatever LLM you have access to. You can have an ensemble of LLMs. You see, your options are almost limitless. However, if you want to learn more about the theory and the code of self-RAG, or you want to see here the code here of multi-AI agent operational, these are my videos I would recommend to you. Of course, the self-assessment can be done by a GPT-4 Turbo visual system. So now we can include here another level of, let's call it, intelligence. But before we do this, I found here by LangChain AI here this very funny illustration here of the complete RAG system. And LangChain AI wrote here yesterday on Twitter, please go there, like it, subscribe, that the RAG system needs to handle here the lower level question that reference specific facts found in a single document, a higher level question that distill ideas that span multiple documents. So you see, RAG has a problem. In general, AI have a problem here of a higher complexity level or a lower complexity level. And with RAG, to handle both types of question can be a challenge if you use here the typical retrieval models. So they developed here a lot of different methodologies for this, which result here in this funny image, but let's have a look at this. The idea is the same. We have an incoming question, we have some stage of preparation, then we go either to a graph database, we go to a SQL database, or we go to a vector store. We augment here this information that we retrieved, then we can filter it, and our main LLM provides an answer. You see, the same process as always. Now, let's have a look what the LangChain community provide us on pre-produced code sequences for each step. So the first, of course, the question that comes in, the system might look at this and say, hey, I don't like this question. I have to translate the question into a form that is better suited for me as an AI, as an LLM. So we have a query translation and the input question is translated to something completely different. Do you think that there could theoretically be already a first mishappen? Second step, you have to choose your database. You have a routing, logical routing, semantic routing. You choose your database. This is a rather simple process. And then, if you have a SQL database, you need a text to SQL LLM, or you have a self-query retriever. Whatever database you have, you need to be able to have an input and an output so that you can query the database. Beautiful. If you have a vector store, there's something beautiful happening because now you encode human sentences into specific vector structures in a high-dimensional vector space. So what do? You take a sentence and you split the sentence. This is called a chunk optimization. Either you chunk at the words, or you chunk at paragraphs, or you chunk at characters, whatever you use, a semantic splitter. Then you have a multi-representation and indexing. You go here to specialized embeddings. Here you know the classical BERT or the sentence BERT, and now I can recommend Cole BERT. This is a beautiful thing. You just have an index, and an index tells you, hey, on page number 412, there's this and this and this. So if you open a book and you have at the very beginning the index, this is happening now also for our tokens. So you have here an index for a vector store. Beautiful. Then, if you have performed your query, you come back and we have now a filter operation. Now, you can have a re-ranking, as I showed you already. You can have a fusion with other information. You can have a CREG structure. Whatever you want. There are a lot of methodologies. And then finally, we can go on and have here our primary LLM. And there we have now the generation of an answer. But also here we can have in our active retrieval, we can have a control loop, a control cycle with a self-RAG system. So the RAG system now analyzes its own performance. It looks itself in the mirror. So you see, you can build here a complexity that's really crazy. And you just want that the answer is the correct answer to the question that stands at the very beginning. Beautiful. But now we go a step further. We want to do more. We have here interactive agent system. So our GPT-4 Turbo visual system looks at this and says, oh, okay, I see. I could here in the SQL database here, there are just some data, but there are some data missing. So in order to provide here this specific query, I can now generate syntactic data and fill up, since I'm a GPT-4 system and I know maybe everything that the human has ever written down, I can now generate syntactic data and I fill this syntactic data here in the database. Or our GPT-4 tells us, hey, I'm also a logic LLM. Therefore, I look at this agent and I look at this agent, and I can supervise those agents in their structure. So you see, now we add critical knowledge here for a system for a specific downstream task, like summarization or whatever you have, translation, for example. So we can now generate syntactic data. We can supervise agent. We have the possibility that a huge LLM trains here a much smaller LLM to increase its performance for a given task. So the possibilities that we can build here now with active agent is amazing. If you want some video on this, I have here for the RAG graph system, DSPy. I explain here why here RAG hallucinates, that you understand here the reason why. I've shown you here you need new logic layers from Stanford University, or there is here a new RAG optimization, which is called QuietStar. If you focus here on AI reasoning optimization, this is for you. And if you want to learn about how do we build syntactic data for fine-tuning, there's a beautiful new methodology by UC Berkeley in this video for you. So you see, we build a construct that's extreme complicated, self-reflective, checking, logical, reasoning structures, self-controlling cycles. And this is all that we built just to be able to answer one simple query that the user has to its LLM. So what we discover, if we have multiple agents, those multiple agents communicate between themselves and they reason. And you can listen to their reasoning if you want. Whatever you find, those multi-agent, every agent is specialized on a particular domain. In his reasoning, we have then a specialization emerging in this group of AI agents. So this means with time of learning, we do a learning, we go in merry-go-round, they become really specialized agents in their field for reasoning, evaluation, and so on. So a self-learning process can happen here. And if our agents are intelligent agents that have an LLM or a vision language model, here a further self-induced learning is no problem at all. But remember, our agents work outside of our main LLM. So they are working here outside, but our main LLM here in blue, now the idea is, listen, if we have specialized entities out there, a team of AI agents out there, would it be possible to have here also those agents, those experts inside our LLM? So a mixture of expert system so that we have kind of a coherence between our internal expert and our external experts. Because if you have an agent that delivers back theoretical physics here as an input, and there's no physics expert here or mathematical expert here that would understand the input that comes in from the RAG system, the system is not able to provide here an intelligent answer. So we want to have kind of a coherence now here of the ability of our agent and the understanding of our LLM. Simpler talked than done, but the idea is clear. We have here a mixture of expert system as our main AI system. And in our LLM, we have here multiple experts that are specialized here for different tasks. We know that GPT-4 is one, Mixtral is one, Databricks Oryx is one, Jumba, a hybrid system of a transformer with self-attention, plus an SMM is one. So mixture of expert systems, think of them as an AI team. Beautiful. Yeah. And the idea is here is superhuman if we come back here to the origin. And this is what I just took here. This figure is here our best robot that we have currently. Beautiful. Now, on the economic side, we encounter a problem. And I have here from Axios, March 27, 2024, the letdown, the hype hits a rocky reality. And this is just one of the articles that argue no one wants to build a product on a model that makes things up. The core problem is the generative AI models are not information retrieval systems. They are synthesizing systems with no ability to discern from the data it's trained on unless significant guardrails are put in place. And even then, this technology is seen by some people as a party trick. So you see, we have a problem that the system is not producing 100% precise, reproducible, transparent results at all time. We have in this system here hallucination at all different levels of LLMs, and even our vector spaces and our retrieval can produce wrong results. So you might say it's not a solution to increase the complexity of the system architecture, or should we find new solution? And I have here a study by Google and Stanford University. And this is the end of March 2024. And they go here and they examine here the long form factuality. So the long sentence facts if it's really correct what an LLM generates. So they verified that the answer of an LLM is true, is correct. And they do this, and beautiful study, have a look at this. And you know what is amazing? Yeah, there's the code, GitHub, Google DeepMind, long form, Factuality. Go there, you have the complete data set, you have the algorithm. Have a look at this, it's really nice. But you know what is really amazing? After we built this complex system from LLM and multi-LLM and multi-AI agent and multi-vector store and normal store and internet connectivity, and it's still not working 100%. Now, Stanford and Google propose here as the latest technology solution for a search-augmented factuality evaluator, SAFE, that at the end you use a Google search to validate each and every result. I mean, this is amazing. Now, in March 2024, Stanford and Google come up and say, you know what we find has really good results? At the end, if you use Google search to find the answer. So I tried to have here this image. Imagine here Microsoft. And then in Microsoft, you have your GPT-4 Turbo here in the core, and then you have built your RAG system with whatever complexity they have. And then they have built guardrails and walls and limitations and logic filter and whatever, just to make this whole thing operational, that if you have a query to an LLM, that you get a correct answer that is factual correct. And now all of this, after years and millions and billions of investment, the current latest technology is, and at the end, you do a Google search to find out if the LLM tells you the truth. This is amazing, and here's a little bit about the methodology they used. But hey, we were talking about superhumans. And it is that in this particular study, there is our superhuman performance mentioned. And this is what the press and some other, I don't know, on the platform suddenly hyped. What they say is simply, we demonstrate that our new methodology achieves, and now it's a unlucky wording, a superhuman performance. Because, yeah, the machine is better than a human with evaluating here the cases. You might say, who would use the term superhuman? My goodness. But hey, everything is about hype here on internet platforms, so no problem at all. And I thought about, you know, me too. I experienced this superhuman performance. And it happened when I was 8 years old, and my father gave me his calculator. And I remember precisely, it was a Texas Instrument 59. And this machine could do things I could never calculate in my mind. Sinus, tangents, hyperbolicus. It was unbelievable. It was even programmable with some magnetic stripes. So when I was 8 years old, I experienced personally superhuman performance as Stanford and Google describes it. So therefore, I can tell you, some time passed, and I experienced superhuman performance, and I'm still here, I'm still fine, the world is still turning, so it happens every day. But let's come back to the main idea, because this is the reason I do this video. The idea of reducing complex information, to divide it, to further divide it, to even go further, to subdivide it into simpler, more manageable pieces. Here's a foundational principle in AI. We break down here a complex query into smaller, more easily solvable parts, and we hope that we come to a solution, and then we are able to put the puzzle back again to find an answer. Now, you know, there are problems that are inherently complex and cannot be simplified, just NP-hard problems if you know about mathematics. And in complex systems, and this is especially in biology, in physics, in social sciences, and, the components of the system are highly interdependent. So the behavior of a whole system cannot be understood merely by analyzing its part in isolation, because you have continuous interaction between the parts of the system. And therefore, this way forward of dividing complex problems in more simple problems, reducing the complexity and adding more non-complex systems is not really the way forward. It is something that we use currently, but we have to have a much better idea. And this is also related to the concept of emergence in complexity theory, where the whole exhibits property its parts do not have on their own. So we use this just here as something that we need to do right now because we have no better solution, but we know it is not the final solution. And there you have it. This was it. What is superhuman and what our internet platforms are hyping currently, and what my subscriber wrote to me. What is happening with superhuman AI? Now you can be absolutely relaxed. Now you know exactly where this comes from. And I say ciao, and it would be great to see you in my next video.